So this is Jeff Hamrick at Rhodes College, and when we last concluded our discussion, we had just estimated the lower bound for a confidence interval for the true mean body temperature based on the results of a study of 130 individuals. We now want to estimate the lower bound of the confidence interval, and so let's get started on that process. So here's a quick heuristic that you can use to speed up the process by which you hunt down the lower bound using your using this trial and error method. If I compute the distance between the actual sample mean body temperature from the data and what we found to be the upper bound of the confidence interval, let me compute that distance. It's 98.37 degrees minus 98.2492. That distance was roughly 0.12 degrees. And basically, because the randomization distributions in this class will often be approximately symmetric, a pretty good guess for what the lower bound of the randomization distribution will be would be 98.2492 minus 0.12, okay? Or roughly 98.12. So I'm going to check out values like 98.13, 98.12, and 98.11 initially. Okay, maybe that will be wrong, but I sort of doubt it given the symmetry of the randomization distribution. So what I'm going to do is change my formula again. I'm going to right-click, edit the formula, and now change this to, let's say, 98.13. I'll press OK. And there are some things that are going to be messed up when we've done this because we have to modify the formula for our empirical p-value. Our blue line, which represents the sample mean with respect to the original set of data, is now in the right tail of the randomization distribution. And when we check out the empirical p-value, the situation seems quite messed up. It's now 0.966, so when you double it, you don't even get a quantity that can reasonably be interpreted as a probability. That's because we need to change the formula for the empirical p-value. We need to switch the direction of this inequality from less than or equal to greater than or equal to, because we want to sweep out the probability mass in the right tail right here. So I did that, and I'm going to press OK, and now this is an empirical p-value we can work with. Now, when we take 0.034 and double it, we exceed our threshold value, our significance threshold, of 0.05. So we would not reject the null hypothesis that 98.13 degrees Fahrenheit is a plausible mean body temperature. That means we need to continue hunting for the right boundary here. So let's check out 98.12 really quick. 98.12 98.12 produces an empirical p-value of 0.023, which when we double gives us a quantity that's underneath the threshold value of 0.05. So the data provide enough evidence to suggest that the true mean body temperature is not 98.12 degrees. That means it's probably the case that 98.11 degrees is not a plausible true mean body temperature, but let's just check that out real quick to be certain about that. If I change this to 98.11, rerun the entire simulation, check out the empirical p-value, it's 0.012, double that, it's less than 0.05. We will reject the null hypothesis that the true mean body temperature is 98.11 degrees. Let me just check really quickly one more time, 98.13, so we can be confident that our results sort of aren't just due to random chance. Of course, every empirical p-value is generated by a random simulation. You could do that. You could keep doing these things over and over and possibly get different answers. But what we see here is, once again, that this empirical p-value is 0.03233. When we double that, we get a value that exceeds 0.05, which means we would not reject the null hypothesis that the true mean body temperature is equal to 98.13 degrees. So I'm going to copy this statement and modify it a little bit. The lower bound of our confidence interval is 98.13 degrees Fahrenheit. Okay? Now notice that arbitrarily I decided to estimate a lower bound and upper bound for my confidence interval to 2 decimal places. There was no particular reason for me to do this. I could have done 1 decimal place of accuracy or three decimal places of accuracy. That would have taken a lot more work. You should look on a quiz or test to our instructions as to how many decimal places of accuracy we'd like to see. If you guys have any questions about this process, it's a little bit tedious, come see us during our office hours.